So we've been talking about normal distributions. Today we're going to talk more about something called a sampling distribution. And essentially what this is doing is it's making a conclusion about the population. And the way that it's doing that is instead of taking a single sample, we're going to take multiple samples and then, for example, find the mean of each of those samples and find the mean of those. And that will tell us the mean of the population. So, for example, right now they're doing antibody tests to try and determine how many people have actually had the coronavirus. So what they're doing is they're taking data from a single sample of 2,000 people. Sometimes it could be more accurate if instead of working with a single sample, we took lots and lots of different random samples and we found the statistics based on those samples. And the key here is that the sample size of each of those needs to be the same. So this is what we would call a sampling distribution. And what we're going to do in this lecture is I'm going to go through, write down what a sampling distribution is, write down some of the things that are key to a sampling distribution, and then we're going to talk about how it relates to the normal distribution, because it does, and we can do a lot of the same things that we do with the with a normal distribution. We can do the same things with the sampling distribution. Okay, so the probability so let me start with this idea that we can take that we could take many different random samples to help us approximate what's going on within a population. So we're looking at statistics from a group of samples, and I'll add in there random samples. So the fact that the samples are random is really important. Remember, that's one of the ways that we help determine reliability. The sample, sometimes you don't want a random sample, right? But in most cases, you do want random samples, especially if you're going to use it to approximate a population. So it's important that when we look at sampling distributions, we're talking about a series of random samples. And all of the samples have to be equal in size. And that size we refer to as n, and that's not surprising. That's something that we've been doing from the very beginning. So for example, okay, take a look at this diagram. If we have a set of samples, so this is random sample 1, I'm going to redo that because there's not really enough room and I'm not sure if you can read it. Okay, and each of these represents a random sample, so that's random sample 1. We could have another one. This might be random sample 2. So I'm abbreviating random sample just as RS. And you can have samples that have the same things in them. You could have overlapping samples. And the reason why you can have these overlapping samples is because they are random. So if we go into a population, so the way that they're doing the antibody testing is they're going into different grocery stores and they're randomly choosing people from those different grocery stores. Now let's say that they're going to a grocery store on 88th Street and they're going to a grocery store in Tribeca, okay? So it might be that on Tuesday, you happen to be in the supermarket, in the grocery store that's on 88th Street. And on Thursday, you happen to be in the grocery store in Tribeca. And it just so happens that in both cases, they ask you for to do an antibody test. So sometimes it can overlap just because you're taking from the same population. That can absolutely happen, and that's okay in a sampling distribution. You can have a piece of data that exists in more than one random sample. So let's write that down. And again, these samples are taken from the population. Okay, so what does this mean? Okay, well, what we're going to concentrate on is taking the mean from all of these different samples. So we're looking at the mean and the standard deviation. And we're going to use that to approximate the mean and the standard deviation of the population. And actually, in most cases, we're going to go backwards. Okay, so let's write this down. The sampling distribution, well, okay, so I'll put this down, but I think that it's going to make more sense in a few minutes. So I'm going to write it, and then we'll explain it as we go. Okay, so the first thing is that when we talk about the sampling distribution, we're talking about a probability distribution still. So the probability distribution for a sample statistic, and we're going to concentrate on mean, this is what the sampling distribution is. Okay, we'll do an example of this, but essentially what we're saying is what is the probability that each mean will occur in all of the different samples? Okay, so if we're saying we're going to take a sample, we're going to take samples of size 10, and what are the samples? The samples are how quickly you drive on the FDR. Okay, what's your speed on the FDR? So for each person, we're going to take their average speed, okay? And we're going to take the probability that that's the average speed for a given person. So it might be, the reason why we call it a sample is because we're not taking a single speed for a person. We might be taking your average speed over a period of time. So the 20 times that you go on the FDR, we're going to take your average speed. And then we're going to do the same thing for another person, and the same thing for another person, and the same thing for another person. And the probability distribution would be based upon the frequency of the different speeds. So just like we did in our last unit with probability distributions, where we said, okay, let's find the probability of this happening. Let's find the probability of this random variable, probability of this random variable. In the case of the speed that you drive on the FDR, in that case, your random variable is the different speeds, and then your probabilities is the probability that that speed is going to occur. What is that based on? It's based on a survey. Okay, just like our regular probability distributions. So the probability distribution for sample statistics, such as the mean, so we don't have to take the mean speed for everybody, we could do something else, but we're going to concentrate on mean, is called the sampling distribution. So when we do this, we call this the sampling distribution of sample means. So if we use the mean as our statistic, it's called the sampling distribution of sample means. And again, this will become a little bit clearer when we do an example. And this is really what we're going to be working with throughout this lecture. Okay, so there are two things that are really critical to the sampling distribution of sample means. Okay. And we're going to be using this a lot. So the first thing is that the mean of the sample means the way that we would write this symbolically is we would have the mu, we know that that's mean, and we have as a subscript x bar. So we know that x bar is a sample mean, right? So this is saying the mean of sample means. In other words, if I wanted to know the average number of hours that you spend on your studying for your statistics exam, okay? I'm going to take, let's say, 10 of you. And I'm going to ask you, how much time do you spend studying for your statistics exam? Okay, so here's the first 10. I'm going to take the mean of that number of hours. Then I'm going to do the same thing for a different number of 10. I'm going to randomly choose another group of 10. I'm going to take the mean number of hours that that group spends. Then I'm going to take another group of 10, and another one, and another one. This is taking the mean of the means from each sample, okay? So we take the mean of every sample and then we average those. That's what this is. So I'm going to use the average here just because I don't want the word mean becoming overwhelming. It takes the average of the means from each sample. Okay, so let's continue here. What we were saying was the mean of the sample means, which we call mu x bar, is the population mean. So the mu x bar takes the average of the means from each sample, and what we're saying is that when we do that, that's really the mean of the population. We're saying that if I took all 33 of you, I think there are 33 of you in this class, if I took all 33 of you and I asked all of you the number of hours that you spend studying for statistics test, the average that I get of those numbers, that's going to equal if I took the average of each of the means from the different samples. Okay, so that's what we're talking about here. Now, we could say the same thing about the standard deviation, except it's a little bit different. Okay, so let's put that in. The standard deviation of the sample means and not so surprisingly, that is abbreviated as sigma and then the x bar. So sigma, if you remember, is standard deviation of a population, and we're going to use subscript of x bar because that takes each of the means from here and it finds the standard deviation of all of those means. So we take the mean from sample 1, the mean from sample 2, mean from sample 3, mean from sample 4, mean from sample 5, and then we use that standard deviation table in order to find the standard deviation of those means. Now, that's not quite equal to the standard deviation of the population, okay? It's equal to the standard deviation of the population divided by the square root of the sample size. In other words, as a formula, the standard deviation of the sample means is equal to the standard deviation of the population over the square root of n, which is our sample size. Okay, this is referred to as the standard error of the mean. That you can't see. Okay, we'll put this on another page. Standard error of the mean. It's just another term that we refer to it as. Okay. Okay, so let me just explain this one more time to make sure that everybody is okay with it. Okay. And then we'll do an example where we actually find the sampling distribution. Okay. And I'm not going to concentrate on your finding the sampling distribution that much. I just think that it'll give you a better idea as to what it means. Okay. So just to give you an idea as to what we mean by the sampling distribution, I'm going to go through that example with the average number of hours that you spend studying for a statistics test. Okay, so we'll say specifically for your test on distributions. Okay, so suppose we want to determine the mean number of hours a student spent, okay, and student in Mat 150 spent studying for the distributions test. Okay, we can take, let's say, 8 samples. Of 10 people and ask them how many hours they spent studying. Now remember, one student may be included in more than one sample. Okay, that's possible. It's a random sample, so it's okay. Now, once we do that, what we can do is we could take the average of each sample. So we take the average number of hours of the 10 people in each of the 8 samples. Mean is the more accurate word because it's very, very specific. Average can be a little bit more vague, okay? Mean is numerical. So we might say that a certain person's ability, artistic ability, is average. There's nothing measurable about it, whereas mean is numbers, okay? It's a very specific definition. So we take the mean number of hours for each of the 8 samples. Then we take the mean of those 8 numbers. So in this step, we're taking the mean of the 10 numbers, whereas in this step, now we have a mean for each sample, and we're going to take the mean of all of those. This is what gives us the mu x bar, okay? Then we take the standard deviation. Of those 8 numbers. And that would require the chart. And that gives us the sigma x bar. Okay, now these are the 2 big things. Okay, this is the same thing as what we did here. I'm just rewriting it, okay, as one quick, like, here's the formula, here's what it is. This is saying that the mean of those samples, of those sample means, is equal to the population mean. And this is saying that the standard deviation of those sample means is equal to the standard deviation of the population over the square root of n, okay? And that's going to be huge for us. So I'm going to put it right in the middle here, and I'm going to box it. because we're going to be using this a lot. Okay, so let's do an example. And in this example, we're kind of going to work backwards, and we're not going to work through everything. So for example, we're not going to find the standard deviation. You already know how to do that. What we're going to do is we're going to just create a sampling distribution from the different information that you're giving. Okay, so we're going to take an example. And we're going to work, like I said, we're going to work backwards. We're going to work from some information that we already know. Just so that you see how it would work. Okay, typically what you would do is you would actually go around and ask people. Okay, so suppose that we have 4 people. The PPL is people. And we ask them how many times they go grocery shopping in a month. So we already know the answers to this because we're asking them ahead of time. So they say 1, 3, 5, and 7 hours. Those are their answers. Okay. Okay. So we're going to use the sample size of 2. Your sample size could be anything. Obviously, the larger the sample size, the better. But I don't want to overwhelm you with too many numbers. So we're using small numbers. Okay. So the first thing that you're going to do is, so sample sizes of 2 with replacement. Meaning you could ask the same person twice. So what we're going to do is we're going to create a table of what the different answers could be. Okay, so let's do that. We're going to have, so let's create a table, and the first table is going to be the answers, the first row. The answers given by the 2 people. And then the second row is going to be the mean of those answers. Okay. And the number of samples is going to be every possibility. Okay, and that means that there are going to be 16 possibilities because we're choosing we have 4 choices for the first person that we ask and 4 choices for the second person we ask with replacement. So fundamental counting principle says we multiply. 4 times 4 is 16. Okay, so there are going to be 16 possibilities in this table. So we're going to take every possible sample of 2 people. This is just our data collection, okay? We're just collecting data, and the idea is that you were given the answers 1, 3, 5, and 7 ahead of time, just so that we can figure out what all of the different possibilities are. For most, when you actually collect data, that you're not going to be given that data ahead of time, right? You're going to actually have to ask people. But because we don't have people to ask, we're saying, okay, well, here are the things that they are going to answer. Let's use that, okay? So, for example, let's say that the 2 people that we choose, the first person says 1, and we happen to choose the second person also, the same second person, so we get an answer of 1 again. These are their 2 answers. Okay, what's the mean of those answers? It's 1 plus 1 over 2, which is equal to 1. Okay. Then we have another possibility, right? First person says 1 hour, the second person says 3 hours. Right? We know that these are the only possibilities because we were told that people are going to say either 1, 3, 5, or 7. Okay, one of the people says that they shop once a month. Another one of the 4 people says they shop 3 times a month. Another one says 5 times a month. And the last one is going to say 7 times a month. So if we randomly choose a sample of 2 people, in this sample, the first person says 1, the second person says 3. What's the average of the number of hours they spend in the store? 2 hours. Okay, then we take another, and the order of this doesn't matter. We're doing it in a very logistical order, just so that we don't miss any of the different possibilities. So we take another random sample, and we have 1 and 5 as the answers. And if we do 1 plus 5 over 2, we get 3. Then we have 1 and 7. So 1 plus 7 over 2 gives us 4. Okay. That's all of the samples where the first person is the person who says 1. Okay. Now we have another random sample where the first person is the person who says 3. So we have 3 and 1. 3 plus 1 over 2 is 2. Then we have the case where the person says 3 and 3. 3 plus 3 over 2 is 3. Then we have the next case where the person says, first person says 3, second person says 5. 3 plus 5 over 2 is 4. Okay, and for the rest of them, I'm not going to write out how we found the average. I'm just going to write the average. Okay, so let's continue. Then we have the next person says 3 and 7. That's the next sample. So 3 and 7 is 10 over 2 is 5. Okay, that's all of the different samples where the first person is the person who says 3. Then we're going to do the same thing for 5. So we have 5 and 1. We have 5 and 2. We have 5 and 3. And we have, I said 5 and 2, but it's not 5 and 2. It's 5 and 3, right? Nobody says 2 as an answer. So it's 5 and 3 and 5 and 5. and 5 and 7. And then finally we have it where the first person is the one who says 7. So we have 7 and 1, 7 and 3, 7 and 5, and 7 and 7. Okay, and if we take the averages, so this is answers, and this is mean. Okay, it's just continuing from up here. That's all that's happening. So 5 and 1 is 6, over 2 is 3. 5 and 3 is 8, over 2 is 4. 5 and 5 is 10, over 2 is 5. 5 and 7 is 12, over 2 is 6. 7 and 1 is 8, over 2 is 4. 7 and 3 is 10, over 2 is 5. 7 and 5 is 12, over 2 is 6. And 7 and 7 is 14, over 2 is 7. Okay, so to find the sample mean, all we did is we averaged the two numbers. Okay, so first of all, let's find the mean of the sample means. Okay, this is simple enough. So the mean of the sample means would be if we took 1 plus 2 plus 3 plus 4 plus 2 plus 3 plus 4 plus 5 plus 3 plus 4 plus 5 plus 6, and then plus 4 plus 5 plus 6 plus 7, and we divide it by 16. This is not the only way to do this, okay? This would give us the sample means. So essentially what we're doing is we're taking the mean of all of the numbers in this second row, okay? And we should get 4 for this. Okay, but this isn't the only way to do it. This is not the sampling distribution. This is just the data collection. So let's find the sampling distribution, okay? The sampling distribution is the probability distribution for this. And we could find the mean using the probability distribution. Okay, essentially it's the second row, right? So our first column, our first row is X bar, and then we have the probability of X bar. So what are our different sample means? Well, we could see that one of the sample means is a 1, right? We're essentially looking through here and we're saying, what are our different numbers? So 1 is a possible sample mean. Okay, this is X bar. This is X bar. Okay, so 1 is a possibility. What's another one? 2 is a possibility. We see 2 there. We see a 3. We see a 4. We see a 5. We see a 6. And we see a 7. These are the different sample means that we see. So now we're going to create a probability distribution. So the total number of samples that we have is 16, right? So the sum of the frequency is 16 because we have 16 samples. So now we have to say, okay, well, how many times does 1 occur? I see 1 only one time throughout here, okay? So this is going to be 1 over 16. And 1 over 16 is 0.0625. Okay, where did the 0.0625, where did the 1 come from? So it's 1 over 16 because 1 appears one time as the sample mean. So it's the frequency. How many times does 1 appear in our second row? Now we can do the same thing with 2. We're counting the number of 2's. I see 1 2, and I see 2 2's. 2 appears twice. So this one is 2 over 16, or 0.125. Now we're going to do the same thing for 3. How many times does 3 appear? I see a 1, 2, 3 times that we see 3. So 3 over 16 is 0.1875. Okay, so this top number is not X bar. That's not what it is. The top number is the number of times that X bar appears, okay, in the second row. So it's not X bar, it's the number of times that X bar appears. So for example, the next one is 4 out of 16. 4 happens to appear 4 times. So it's 0.25, but you'll see 5, I just wrote it wrong. 5 doesn't appear 5 times. 5 appears only 3 times. So this is 3 out of 16 again. 6 only appears twice. So this is 0.125 again. And 7 only appears once. So it's 0.0625. So a couple of reminders, okay? The top number, or the numerator, in P of X bar is the number of times that mean occurs. It is not X bar, right? And I mentioned that because it's confusing for the first 4, right? For the first 4, it looks like it would be X bar, but it's not. It just so happens that 1 only appears once, 2 only appears twice, 3 only appears 3 times, 4 only appears 4 times, but then 5 appears 3 times, okay? So that's something to take into consideration, okay? This is the probability distribution. So the second thing to remember is that the sum of P of X bar has to equal 1 And every P of x bar is between 0 and 1. It's a probability distribution, so we have to remember that. Okay, I think everybody got that correct on their quiz. So on their last quiz. So these are the two things to remember. Okay, if we were to graph this, it would be perfectly symmetrical. Okay, so if we were to graph this, you would have 0.0625 on each side, 0.125 on each side, 0.1875 on each side, and 0.25 in the middle. So this would be perfectly symmetrical. So if we were to graph this, it would be symmetrical. Okay, and so we're not going to take the time to do that. One, because you already know how to do it, and two, I don't want to take the time in this lecture. It's not important enough, okay, for me to actually go through and graph it. What's important for you to see is that it does become symmetrical, and the more samples that we do, even if it's not symmetrical with a small number of samples, it becomes more and more symmetrical with a larger number of samples, okay, which we'll discuss in a minute. But so a couple of notes here, okay? We're not going to take the time to do these things. We're just making these notes. So if we were to graph the probability distribution, which is now sampling distribution, right? Remember, it's only a sampling distribution if the data that you're taking is from samples and different samples. It would be symmetrical, and it would approximate a normal distribution, which is what we're going to be looking at for the rest of this lecture. Okay, now the other way to take the mean here, right? If you look at what we did on the previous page, you could find the mean by doing this, okay? Or we could find the mean the way that we take the mean of any probability distribution, okay? Where we take the sum of the x bar times p of x bar. Okay, and this is also equal to the mean of the population. And so the mean of the population is 1357, right? 1 plus 3 plus 5 plus 7 over 4. That's the mean of your population. The mean of your sampling distributions would be 1 times 0.0625 plus 2 times 0.125 plus 3 times 0.1875 plus 4 times 0.25 plus 5 times 0.1875 plus 6 times 0.125 plus 7 times 0.0625. Okay, and in both cases, you would get 4. And then the last thing is, and we are not going to create the chart for this. So this was equal to 4. Okay, this is also equal to 4. They wind up equal to each other. And then the last thing is that the standard deviation is the same thing as the standard deviation over the square root of n, which in both of these cases, if you actually go through and do the work, it's 2.2. Okay, so in this case, we would find the standard deviation of the probability distribution. In this case, we would find the standard deviation of the 1357 only, okay, using a mean of 4. So I'm not going to go through those charts because they're long and there's no reason for it. But if you were to find it, in both cases, you would get 2.2. And that's really our goal here, to show you that if we took a sampling distribution of any 2 people from that group of 4, we would get a standard deviation of the sample means that would be the same as the standard deviation of the population. Okay. Okay. So let's move on. Okay. And the next thing that we're going to talk about is something called the central limit theorem. And this is where we start taking sampling distributions and relate them back to the normal curve. Okay, so all of this relates back to the normal curve. I'm going to write it as simply as possible. If you want really mathematical terms, then you can go to a textbook, you could go online, and you can just look up central limit theorem. You'll get these nice complicated things. I'm going to try and keep it very, very simple. And again, this relates the sampling distribution of the sample means in the population that the samples are taken from. Okay, so this is it's not really separate, but it's looking at it from another perspective. So the central limit theorem. Okay, what does the central limit theorem do? It tells us the relationship between the sampling distribution of sample means and the population that the samples are taken from. Okay, so there are 2 parts to the central limit theorem. The first thing is if the random samples have sizes greater than or equal to 30, okay, so if our sample size is greater than or equal to 30, okay, then the distribution of sample means approximates a normal distribution. So the bigger the sample size, the better. Okay, and again, what does this mean? U of x bar is equal to mu, and sigma of x bar is equal to sigma over the square root of n. Okay, so we can use that. So what we're saying is if we have sample sizes, if we're taking samples that have a sample size of greater than or equal to 30 people, then we can use all of the information that we know about normal distributions that we've talked about in the last 3 lectures. We can use all of that to help us do any sort of calculation, any sort of probability. We can use the fact that it's a normal distribution. Okay, that's the first thing. The second thing is if our samples are drawn from a set of data that we know is normally distributed, okay, then it means that the sample means are also normally distributed. And it doesn't matter what the size is. So in other words, here, the data that we're taking the samples from doesn't have to be normally distributed. It becomes normally distributed as long as n is greater than or equal to 30. Okay, so here we have to look at the sample size because the data isn't necessarily normally distributed. Now in the next one, so I'm going to actually add in here because this is kind of a big thing. Even if the original data is not normally distributed. Okay, so again, here we're saying if we're pulling out samples from the population that are bigger than 30 people or 30 things, 30 objects, whatever it is, then when we take the sampling distribution of the sample means, we're going to get a normal distribution. Okay, the second piece is if the data is normally distributed, we don't care about the sample size. The sampling distribution is a normal distribution. So if the original data is normally distributed, then the distribution, I really should say sampling distribution. The sampling distribution of sample means approximates a normal distribution. Regardless of sample size. So n could be anything. N can be any number. And once again, this is still true that mu x bar is equal to mu and sigma x bar is equal to sigma over square root of n. So that's still true. So in one case, if we're trying to approximate a normal distribution, we have to look at the sample size. And in the other case, if it tells us that the original data is normally distributed, we don't care about the sample size. Okay, so let's apply it. And now this is very straightforward. And it's stuff that we've actually, a lot of this is going to wind up being stuff that we've done before. Okay. Okay, so let's take just different examples. So we have a study that analyzed the sleeping habits of college students. Okay, they found that mu is equal to 6.8 hours, and sigma was equal to 1.4. Okay. Okay, so the first thing that we're going to do is we're going to take samples of 100. From the population. And we want to do two things. We want to find the mean of sample means, and the standard deviation of sample means. Okay. Well, we know how to do this. Okay. The mean of sample means is equal to the mean of the population. Which is 6.8. Right? Pretty straightforward, pretty simple, not a problem. And the standard deviation of sample means is equal to the standard deviation over the square root of n. Well, the standard deviation is 1.4, and our sample size is 100. So what does this give us? 0.14. And that's it. And we're going to say, okay, n is greater than or equal to 30. So the sampling distribution approximates a normal distribution. This is not critical for this particular aspect of finding data, okay, of finding the mean of sample means and the standard deviation of sample means, but I want you should be getting into the habit of looking at this. So n is greater than or equal to 30, so the sampling distribution approximates a normal distribution. Okay, let's take a second part of this. Let's say that instead of taking samples of 100, we take samples of 64. Okay. we're going to do the same thing. We find the mean of sample means. And the standard deviation of sample means. Okay, again, we know how to do this. Notice that our calculations are really straightforward. They're not difficult at all. They're not long. They're just, I mean, when we find the mean of sample means, there's not even a calculation, right? Mu of x bar is equal to mu, which is 6.8. That doesn't change because that's not dependent on our sample size. Now our standard deviation of sample means is 1.4. And this time, instead of taking the square root of 100, we take the square root of 64. And this gives us 0.175. Okay, so just a note, the answer in part A is going to be more accurate. Because our sample size is bigger. Okay, the bigger the sample size, the more accurate our answer is going to be. Okay. Okay. Let's take another example. So okay, again, I want to note this again. That n is still greater than or equal to 30. So the sample distribution, the sampling distribution approximates a normal distribution. Okay, and we're looking at this because it doesn't say that the original study that this is normally distributed. So if it doesn't say that, we want to look at the sample size. Okay. Okay. So another example, simple example. In fact, it takes a lot longer to write the example than it does to write out our answers, right? So training heart rates for 20-year-old athletes are normally distributed. So this means we don't have to look at sample size. With a mean of 135 beats per minute. And a standard deviation of 18 beats per minute. Okay. We're going to find U sub x bar and sigma x bar for samples of size 4. So notice our sample size is less than or equal to 30, but it's okay because the data is normally distributed. Okay, and this is easy enough. We know we know mu of x bar is equal to mu, so this is 135. And sigma of x bar is equal to sigma over the square root of n, or 18 over the square root of 4, which is just 9. Okay, and that's all the work that we have to do. So notice it's very little work that we have to do in order to find the mean of sample means and the standard deviation of sample means if we're given this data. Okay. Okay, so let's move on. Let's talk about probabilities. And again, we've done this so often that this is repeat, okay? It's very, very repetitive of what we've already done. So finding probabilities with the central limit theorem. This is very similar to what we've done. And this is where it becomes really important to take into consideration normal distribution. Okay, and in fact, we're going to use the z-score table again. Okay, so let's suppose this is an example. I'm underlining because it's not unrelated to what we did. It's just it's not unrelated to what we did. It's simply just a little bit different because we're using the z-scores. So I just want to indicate that it's different. So suppose we're given the following data. And this data describes the average number of hours that somebody drives, the average number of miles that somebody drives per day. So it's broken up by age. So we have an age group of 16 to 19. So 16 to 19-year-olds drive an average of 20.7 miles per day. 20 to 29-year-olds drive an average of 31 miles per day. 30 to 49-year-olds drive an average of 37 miles per day. 50 to 64-year-olds. Notice these are not equal age groups. That doesn't matter. Okay, we're not doing any sort of graphing. And finally, 65 to 74-year-olds. You're told to drive an average of also 30.4 miles per day. Okay, so we're just going to take some questions. We're going to work through some questions that deal with this data. Okay, so we're going to use this data in order to help us answer these questions. Okay, so the first thing is, suppose we randomly select 50 drivers. Age 16 to 19. And we want to know the probability that the mean distance traveled is between 19.4 and 22.5. miles given a standard deviation. So notice you're given a standard deviation of 6.5. Okay, so the first thing that we have to check, we're checking for two things. If neither applies, then you can't do this. At least not now. Okay, which is kind of indicative that one of them will apply. So 1, the data is normally distributed. Or 2, n is greater than or equal to 30. As long as one of these is true, you're okay. Okay, how do we know it's normally, whether or not it's normally distributed? The problem will say this, okay? So nowhere in here does it say that the data is normally distributed. This is not true for this problem. Okay? It doesn't tell us this, so it's not true here. I'm going to take this out because that's going to be confusing. This is not true here. So then we have to go to the second thing. If the second thing isn't true, then we're done. We need to make sure that n is greater than or equal to 30. So we have to look at the sample size. What's the sample size? It says we randomly select 50 drivers. N is greater than or equal to 30. This is true. N equals 50. Okay? Because n equals 50, we can go on. And now this is just exactly what we did with our z-scores, okay? So this is saying I'm going to just put in a note. You have to do this for every problem. Every single problem that you do like this, you have to do. Okay. Okay. So the data is normally distributed. So now we can go on. This is asking, okay, what is the probability that 19.4 is less than x bar, which is less than 22.5? Okay. We need to find the z-scores, okay? Now here's the difference. The z-score for this is using x bar instead of x, okay? So this is going to be the same for every problem too. So the only difference is z is equal to x bar minus mu x bar over the standard deviation x bar. Okay? Okay, so what does this mean? This means that in order to find the z-score, we have to find the mu x bar is already given to us. Okay? The mu x bar is already given to us. The standard deviation, the sigma x bar, is already given to us. So we just need to remember that sigma, now this is the same thing, right? X bar minus mu is equal to sigma over the square root of n. So we know two things here. We know for this problem that mu is equal to 20.7, okay? We're only looking at 16 to 19. So if we go to the chart and look at 16 to 19, it's 20.7. Sigma is equal to 6.5. We were told this over here. Okay, so we're going to find the z-scores based on this. And our x bar, we're looking at 19.4, and we're looking at 22.5. Right, this is calculating the probability that something falls within an interval. So this is just like what we did in the previous lecture. Okay, this is repeat. The only difference is that we have to take our sigma and divide by square root of n. Okay, so let's continue. Sigma x bar is equal to 6.5 over the square root of 50. Okay, which in this case is 0.9. So now we're going to do the z-score for 19.4. 19.4 minus 20.7, which is mu, over 0.9. This is negative 1.4. Now we're going to do exactly the same thing for 22.5. Okay, so this is our x, right? We're using x bar, but it's x bar minus mu. Our x bar is 22.5. The only reason why we call it x bar is because we're saying the averaged, that the average number of miles traveled is between this number, okay? This is equal to 1.96. So now how do we find this? Well, what we're saying is that the probability of 19.4 less than x bar less than 22.5 is the same thing as the probability of negative 1.4 less than z less than 1.96. And how do we do this? We go to our z-score table. Here's our z-score table. And we look at 1.96. And 1.96 is 0.975, right? And this gives us the area that's less than 0.975. Sorry, the area that's less than 1.96. This is essentially saying the probability of z less than 1.96 minus the probability of z less than negative 1.4. Okay, this is exactly what we did already. So this is saying at 1.96, the area under the curve is 0.975, probability is 0.975, and then we're going to go to negative 1.4, and we're going to look up that number. We're looking up exactly negative 1.594, so it's this is a negative 1.41. So 1.41 is 0.0793. Okay, so let's just review what we did. We got negative 1.41 here. That's the z-score for 19.4. Then we got the z-score for 22.5. We got 1.96. So what we're looking for is the probability that it falls between those z-scores. So because this is an interval, we take the z-score of 1.96 and we look up the area, 0.975. Then we take the z-score for negative 1.4, look up that area, it's 0.0593. Remember, this is the area of the curve that's to the left of these z-scores, okay? And we subtract and we get 0.8957. This means about 90% of drivers (16 to 19) will drive between 19.4 and 22.5 miles in a day. Okay, let's do one all the way through. Let's do a second case, same data. So suppose we randomly select 90 drivers. But this time we'll use 30 to 49. And our standard deviation in this case is 7. Okay. We want to find the probability that the mean distance traveled is between 32.8 and 40. Okay, so we have our checklist. We have to start with that checklist. Is the original data normally distributed? Second piece of the checklist is n greater than or equal to 30? One of these has to be true. The answer to the first question is no. How do we know it's no? We're not told anywhere that it is normally distributed. Second one, is it true? Yes. What's n? N is 90. We randomly selected 90 drivers. So that means that we could go on with the problem, okay? The answer is no to both. Stop. So we need to find the z-scores for 32.8 and 40. But the first thing that we have to do is find that standard deviation of the samples, okay? We have to do that. We don't have to do that with the mean because the mean is the same, but the standard deviation of the samples isn't. So this is going to equal the standard deviation that we're given over the square root of n. We're given 7, and we're taking the square root of 90. That was our sample size. So I didn't calculate this one ahead of time because I want you to see how to calculate it. Let's see square root here. Okay, so on your calculators, you'll have a square root on your calculators. This one doesn't, okay? So I'm going to show you how to do it just in case you don't have a square root of 90. You're doing 7 divided by, and when you don't have a square root, you can take the number and raise it to the 1/2 power. Okay, that's exactly the same thing. So you're taking the n and you're raising it to the 1/2 power. That's the same thing as square roots. I don't know how many of you know that, but it is the same thing. Oh, we have square root here. So you can see it's the same thing. We have 7 divided by, and then, sorry, let me clear that. 7 divided by, and I'm going to put it in parentheses. 7 divided by, and you type in the number first. This is true for most calculators. Second, and then square root. And you see that we get the same answer. Okay, so it's 7 divided by, and then I would put it in parentheses. In most calculators, you have to type the number first and then you do the second square root, okay? In some calculators, you can do the square root first. I can't really tell you which is correct for your calculator since I can't see it, but my suggestion would be type 9 and then the square root sign, see if you get 3. If you don't, then type the square root sign and then 9 and see if you get 3. And that'll tell you which you have to type in first, whether it's the square root or the number. Okay, and you see that we get we get 0.738. Okay, so now it's just a matter of plugging in. So we have to find the z-score for 32.8. I'm going to do this on the next page because it's a little bit tight here. So we do 32.8. And now we have to go and we have to find the mean for age 30 to 49 because that's what we're working with. So the mean of age 30 to 49 was 37 here. And then over that standard deviation that we calculated, which was 0.738. So we can go to our calculator. 32.8 minus 37, and then divide by 0.738. Okay, hang on, I might have to change these numbers. Let's change these numbers. I'm going to change the problem just a little bit so that our numbers aren't so crazy because that was like negative 5.6. Let me go back. Let me change this to, instead of 32.8 to 40, let's change it to 36.8. Sorry about that. 36.8, and instead of 40, just to play it safe, let's change it to 37.2 or 37.3. Okay, so now we're going to find the z-scores for 36.8 and 37.3. Sorry about that. I just wanted the numbers to be a little bit better. Otherwise, it doesn't demonstrate anything. 36.8 and 37.3. So we're going to calculate the z-score for 36.8. And if we do 36.8 minus 37, that was the average that we're given, and we plug this in, 36.8 minus 37, we divide by 0.738, we get negative 0.27. Okay. And now we're going to do the same thing for the other z-score, which was 37.3. So 37.3 minus 37 over 0.738. We get 0.41. Okay, so here's what this is saying. This is saying that the probability of 36.8 less than x bar less than 37.3 is the same thing as the probability of negative 0.27 less than z less than 0.41. So this should look really familiar because we did this before. So we go to our z-score chart, okay? We have to start with the bigger one, right? We have to start with the probability of z is less than 0.41. And then we'll go to the negative 0.27. So 0.41 is here. It's 0.6591. And then negative 0.27 is here. It's 0.3936. And what do we get? 0.6591 minus 0.3936 gives us 0.2655. And this would be our answer here. Okay. Okay. Let's take, this is the last instance. So in both of these instances, in both of the examples that we just did, our sample was more than 30. Let's take a look at what the problem looks like when it does it in the other way. Okay. So we'll do one more example. Okay, so suppose the room and board expense at four-year colleges is normally distributed. Okay, here we're giving you that the mean is $10,463 and the standard deviation is 1,650. So this is given information to you. You don't just come up with it. It's given to you, okay? We want to find the probability that if we randomly select nine colleges, the mean expense is less than $10,750. Okay? Okay. We're going to do exactly the same thing as before. We need our checklist. Okay? So our checklist is the data normally distributed? Or is n greater than or equal to 30? So let's go to our checklist. Is the original data normally distributed? Yes, it says so. Notice this is how it will look. It will say it is normally distributed. So yes. Let's check the second, even though it's not necessary, okay? N is not greater than or equal to 30. N is equal to 9, okay? It doesn't matter because you said yes to the first one, okay? So we can still go on. So, same thing. We need to find the z-score for 10,750. In order to do this, we first find the standard deviations of the samples, which is standard deviation over square root of n. And standard deviation was given to us. It's always given. And our sample size here is 9. So we're taking the square root of 9. So our standard deviation of samples is $550. Okay. So we need to find the z-score. 10,750 minus 10,463 over 550. What do we get here? 0.54. So here's what we're saying. The probability that X bar is less than 10,750 is equal to the probability that Z is less than 0.54. And this we could just get directly from the Z-score chart. We don't have to do any additional calculations because it's already a less than. So if we go to 0.54, we see that it's 0.7054. And what is this saying? This is saying about 71% of samples of 9 colleges will have a mean room and board expense less than $10,750. Okay, so one very last piece to this. Now that we know how to do these random variables, notice again, this is stuff that we've done before. The only difference between what you did before and what you're doing now is that you have to find the sigma X bar, okay? But you're still given the mean, you're still given a standard deviation, you're still given a range or a number less than or a number greater than, and you're still finding Z-scores. It's just that your first step in finding the Z-score is calculating the sigma X bar. Okay, and of course you always have to do this checklist. Okay, so one last piece. What is the difference in finding, this is pretty much exactly what I said, in finding probabilities. Got ahead of myself there. For one random variable, which is what we've been doing, versus for sampling distributions. Okay, sampling distributions is when you're talking about sample means, right? One random variable is just exactly what it is, a single random variable. So we're just going to do one example so that you see the difference, okay? So suppose for a population of college students, the amount students put on their credit cards for school-related materials or school-related expenses. Is normally distributed. So notice, as soon as it says normally distributed, we don't care about sample size. So if it doesn't say this, we have to look at sample size. Here we don't have to. Okay, now we're going to be given a mean and a standard deviation. So the mean is $615. And the standard deviation is $550. So let's take one where we're not talking about a sampling distribution. We're talking about one student. So we want to know, what is the probability one randomly selected student put less than $1,400 on a credit card. Okay, well, this is not a sampling distribution, so we don't have to find sigma x. And we don't have to go to our checklist. So we don't need our checklist. We can go directly to our z-scores. This is the difference. Okay, this is what we've done before versus in previous lectures versus what we've done in this lecture. Okay, so we're just going to find our z-score. It's 1,400 minus 1,615 over 550 this is equal to 0.39. So notice the difference here. Instead of saying probability of x bar less than 1,400, we just say probability of x less than 1,400. And this is equal to the probability of z less than 0.39. And if we go to our z-score chart, okay, and we go to 0.39, 0.39 is here. Sorry, that was negative 0.39. We're below the mean. Negative 0.39 is right here. It's 0.3483. It's this one. Okay, 0.3483. So I had written 0.39, it's negative 0.39. Okay, and that's our answer. That's it. Okay, versus the question, what is the probability that if we randomly select $25 students, the mean amount put on their credit card is less than 1,400. So notice we're using the same numbers. The question is framed differently. Okay, so this is a sample, okay? We need to do our checklist here. Is the data normally distributed? The answer is yes, it told us that. That was the part at the top here. It means we don't have to look at sample size, so we already answered the question. But I'm putting it here so that you know that you have to, you need to take it into consideration when we have samples. Okay, so is the data normally distributed, or is n greater than or equal to 30? Okay, the randomly select 25 students says it's a sampling distribution. So this is where the difference comes in. Okay, so how do we answer this? Is it normally distributed? Yes. Is n greater than or equal to 30? No, only one of them has to be true though. So here we need to find sigma x first. That's the big difference, okay? So sigma x is equal to sigma over square root of n. Sigma here is 550. N is 25. So this is 110. So now we find the z-score. Z is equal to 1,400. So notice this top is the same. Over 1615, but now we're dividing by 110 instead. And we get negative 1.95. So now the probability, and notice the difference, we're not writing x, we're writing x bar. The probability that x bar is less than 1,400 is the probability that z is less than negative 1.95. And if we go to the z chart here, and we go to negative 1.95, it's less than, so we don't need to do any other calculations. Negative 1.95 is right here at 0.0256. And that's our answer. So that's the difference between these, okay? When it's talking about a sampling distribution, you need to make sure that one of these is true first, and you need to do this, okay? So these are the extra things that you need to do. I'm going to star them in pink. You need to do this, and you need to do this. Those are the two extra things that you have to do when it's a sampling distribution versus when it's a single random variable. Okay, and that's it. And that's it for normal distributions in general. That's the last lecture here. So you'll get a quiz on that on Monday. Okay, and this video will be available through to the end of the week. So all the way through Sunday. And that's it.